Okay, so
You
I
are.
can start. Yeah.
Yes.
All right. Hello, everyone. I'm gonna talk about time series data today. I'm gonna compare SQL Server and Postgres SQL with timescale DB extension from few angles. Um, so yeah, let's get into it. So first, a couple words about myself. I'm Michal. I'm database engineer, SQL Server DBA. I've started as junior DBA almost 20 years ago. I've been through different DBA roles mostly to senior DBA, and for some time even I was running a small DBA team. Now I'm back purely into engineering role. Yeah, so you can find my details here by scanning this code. And yeah, let's get into the session itself. So what I'm going to talk about and what are the goals of this session is to understand how SQL Server and Postgres Plus times DB, timescale DB extension approach the time series data. We're going to compare data ingestion processes in each one of them, evaluating compression ratios, so effectively how efficient storage usage is going to be. We'll compare query performance on realistic market data. And then we will get into showing how complex it is to maintain both solutions as they become production. And at the end, try to make a decision or give some hints to help someone to take decision which of those two will be a good choice for your scenario or your data or your organization. You might ask yourself question, why are we comparing SQL Server to Postgres plus timescale DB? Timescale DB is an extension that requires Postgres SQL relational engine. So we are comparing a targeted time series solution with well-established relational database engine, which SQL Server is, which comes with lots of other features and options. So the reason is obviously my background here, right? So I've been working with SQL Server for a number of years. I know this product. I'm a bit newer to Postgres. I don't know Postgres so much, but at some point I had to work with timescale DB and time series data in both of them. So I think I can present this view on how of both of them behave and operate in time series data world. Okay, so first few words about time series data, what it is, what are the characteristics of this type of data. So we can assume that it's ever-growing data. We have point in times in which we collect the data. It can have different granularity. It can be every second, every minute, every day. Depends on what type of data we are collecting. It is always appended over time, rarely updated. Usually it's not updated at all. And we run analytical queries against this data. So a typical relational model does not fully apply here. I mean, we still have a table that we want to query, but usually we don't build relations with other tables. We just ingest the data over time. We have more and more data, and we need to manage it and query it efficiently. Aggregate via windowing functions, bucketing, rollups, and such techniques. what is the time series data? Some examples. It's all around us today, starting from financial data, like you see on this sample graph on the right-hand side. This is how usually market data is presented. So you have those candlesticks, where which one of them represents an opening price, closing price, and the highest and the lowest price within a specific time frame. As I mentioned, it can be a minute candlestick, an hour candlestick, whatever is appropriate. Also, this can be any telemetry data. So I'm coming from infrastructure world, so it's often very important to collect server metrics like CPU utilization, memory consumption over time. This is also time series data. We can also have readings from different devices. On one of the time series data presentation, I heard that I haven't verified that fact, so I can just repeat what I heard, that Boeing engines collect like couple terabytes of data per hour of flight. So you can imagine how big volumes of time series data can get. Also a funny story on time series data, because I've been asked before the session, how long am I working with time series data? And when preparing this session, I realized that back in the days when I was in primary school, our teacher asked us to record temperature on a sheet of paper, because those days none of us had personal computers. So write down the temperature every morning, every evening, every midday on a sheet of paper, and do this exercise for 2 weeks or a month. Don't remember really. Which we did, and then at the end we had to prepare a chart based on the data we collected. So I didn't realize that back then, but probably this was my first connection with time series data. Okay, so I will explain what our test scenario will be, because I will jump into a lot of demos. Unfortunately, I have to warn you that I will be a bit jumping between different tools, because due to what I'm going to show you, I need dedicated tools for Postgres, which will be pgadmin, and SQL Server Management Studio for SQL Server. This presentation and some graphs, so I will try to make it smooth so it's easy to follow. But yeah, apologies for those context switches in between, but this is necessary. So our data set is collected from New York Stock Exchange. It is financial market, obviously. So stock prices, snapshots taken every 5 minutes. So as I showed you before, on the sample graph, we'll capture this opening, highest, and lowest and closing price for each 5-minute period, and the volume size, which is how much stock, how much shares change their owners during given time, and obviously symbol which will represent the company. The volume of the data we'll be working on will be almost 38 million rows in each engine, so it's exactly same data set loaded into each engine. I will have two tables per engine, just for better comparison. So it will have uncompressed traditional row store table, and the column store compressed one specifically for time series data. I will go into more details shortly. We will ingest the data. I will also demo that in batches, and then we will query. I will run some sample query in each engine, each table to show how quick or how slow it is. Okay, so let's first explain how each engine approaches the time series data. So in SQL Server, we will require, well, this is not required, but this is a good practice, especially if we have big volumes, the technique called partitioning. This requires partition function and schema to be pre-created before we can design our table. So what is partition function and schema? So partition function defines the boundaries for how we gonna group the data. We do it by time, as shown here. So in this example, you can see quarter, which start of quarter and end of quarter defines start and end of each chunk. Then on top of it, we have partition schema, and then we can build, we can design file groups. This is not, this is optional, but also a good practice for big volumes to have many file groups. For instance, if we deal with really big volumes, there's a file group size limitation in SQL Server. So then our table, well, as we go and as we ingest the data based on time column, it goes to the correct partition. Then indexing. We will build clustered column store index on the table to achieve better compression. The compression technique here is data as we ingest it goes to something called data store, which is traditional B3 row store model. And then a specific chunk is being closed. The underneath process called tuple mover closes a certain chunk and compresses it. We call those chunks row groups. There's some maintenance that has to be done, especially when we're using partitions. So we can semi-automate that, but still it requires some attention from a DBA, from person managing the environment, to create new partitions as we go. Maybe switch some partitions or merge older partitions if we find it required. And the querying. Querying, if we're using partitioning technique, allows us to eliminate partitions based on our date and time condition to make the query faster and not read the data we are not interested in aggregating. So next one is our timescale DB. Timescale DB has an idea of hypertables. So hypertable is something that's underneath a traditional table, and it has chunks, right? So same as partitions shown before, those chunks are have size of whatever we choose. It can be a week, a month, a quarter. We define the time interval. Compression, also column store compression on each chunk. Also traditionally, as in SQL Server, the data first goes into uncompressed row store, Then there's a background process that compress older chunks. We define that. We can also define auto drop policies. We don't do any manual stuff here. I will showcase this. Chunk pruning, which is similar to mentioned partition elimination in SQL Server, and time bucketing for our aggregates. Maintenance is done via scheduled background jobs that does not require much attention. So when we create a hyper table, the traditional table becomes like sort of an alias that we call, that we select from, but all the operations underneath are really done on those hyper tables. And column store compression, what it is. So we have our traditional row store where data is stored row by row, as in our example. So we have symbol, time, the 4 values for price, volume, and each row is stored in this manner. So when this is converted into column store, engine, both in SQL Server and in Postgres timescale, it converts columns. The data is stored column-wise, no longer row, to allow the compression. So those values are grouped together and stored column-wise, as shown here. This way, the similar values can be better compressed. Okay, so I think at this point we can jump into some demos. I will start with SQL Server Management Studio. Hope you can see this. I will first explain what our environment looks like. So we have 2 virtual machines. One is running Windows Server with SQL Server 2022. Here you can see the output of the query. It has 4 CPUs and 4 gig of memory. So this is the setup we'll be working on. Similarly in Postgres, the same query, well, not exactly the same because I'm not able to get the hardware details from this query, but it's Postgres version 16 running on Ubuntu 24 with timescale extension version 2.24. The number of CPUs and memory is exactly the same. However, it's not visible from this query, as I said. Such query is not available in Postgres. Okay, so let's see how our tables are built. So we have stock data underscore 5m, so it stands for 5 minutes. The uncompressed traditional table, which consists of these columns, with our primary key consisting of symbol and time, because those are 2 that are defining uniqueness of each row. Now, how do we create a hyper table? So timescale db1. So at first definition is exactly the same, but we add some more to this. So we, having the timescale db extension installed, we can use these parameters. Defining this is a hyper table. This is our chunk interval, 7 days. Why 7 days? To be honest, I didn't know what to start with. as per timescale documentation, 7 days is the default thing to start with. So that this is the main reason why. We enable column store for the table. We use time as our order by column, and we segment by symbol. So the rows are grouped by symbol for better aggregation down the line. Okay, so these tables are pre-created, obviously, with the data already populated. We can add a compression policy, right? So we say that in this table, everything older than 7 days should be automatically compressed. Okay, so let's compare our setup that we are working on the same data. It takes a bit of time to complete. Meanwhile, I will jump into SQL Server setup. So, as I mentioned before, creation of the table requires partition function and partition schema, which has been also prepared before. That requires a bit of a code, so it's separated here. Created a database with some file groups per year, and then we add a file to each file group. Once we have that, we can create our partition function and schema. So partition function defines the boundaries and then the date boundaries, and then partition schema defines to which file group each of those boundaries, each of those groups will go. This code doesn't look nice, right? So it's difficult to write this manually, especially when we have lots of those. There is a way to nicely automate that and create this in a loop, which I will be also showing. But yeah, for now, I just wanted to show you it is there. Our data model. So once we have the partition schema, partition function, we can create tables. So our column store table, we define exactly the same columns, right, as in Postgres, and we create it on our partition schema, and we say this is our partitioning column, so time. This will be partitioned by time column. And once we have table, we can create cluster column store index, where the data compression is column store. Similarly, we created on same partition schema, defining same partitioning column. This is a must. And our raw data table is a traditional row store, so we create a primary key cluster index on symbol and time column. We do not apply any compression. It's created on default primary file group. Okay, so this query has finished. We have 37.5 million rows, both in row store data and hyper table. Let's go to SQL Server, and there's a query that will show us more or less the same. So we have our column store and uncompressed tables, same row count. And also you can see already sizes here. Also, it shows you that our column store is partitioned. It consists currently of 165 partitions, and the total size is around 1 gigabyte, whereas the row store data is slightly over 2.5 terabyte. So that's the difference. few more words about column store in SQL Server. So it is beneficial to insert the data in bigger batches, right? To make the most of our compression, and if we use bigger batch size when ingesting the data, then our data gets compressed and we can bypass the delta store. The optimal and best practice is to insert 1 million rows, around 1 million rows. This is the exact number here. Why this is important? To be honest, back in the days, I didn't know that and didn't realize that. So first, when I created the column store table, I was inserting the data in batches, whichever I wanted, right? And this has created some confusion here, right? So let me show you this query. There's some. Oops, sorry. Let me explain why. So I have created additional table, which is called column store underscore NP. It doesn't have partitioning, but while ingesting the data, I use bigger chunks of data. So you can see that I've managed to fill up each row group with exact the number of rows that one row group can have. It got compressed immediately, and the compressed size is more well, it's more efficient than the chunks that row groups that doesn't have this exact number. So you might need to think about how you ingest your data into column store in SQL Server. Okay. So let's jump into Postgres now, and let's compare how it looks from this side. Let's compare the size of both tables. So we have our hyper table, which has nearly zero size, and we have our uncompressed raw data, which has around 4 gigabytes of size, both index and data. Why this is not showing anything? Because once we convert it to hyper table, the data is actually stored elsewhere and it's not showing anything here. So we need to take a look at internals of timescale. This is the query that will show us the size of each chunk. So as you can see, here is where the data lives. In timescale creates additional schema where the compressed chunks are stored, and you can see here uncompressed size and compressed size and the compression ratio for each chunk. To have the overall view of all the chunks together, we have another query that shows us number of chunks, the total size before compression and after compression, and our compression ratio. The before compression slightly differs from our raw data table. Here we can see it's around 5 gigabytes. There was around 4 gigabytes. I'm not sure why, to be honest. I didn't get to the bottom of it. Why it's calculating differently. But here it says our compression ratio is around 24%. So timescale in many documentation says that we can count on compression up to 10% of original size, sometimes more. We didn't achieve that here, probably because our data looks like it looks, and it could. This is the most it could get. So I will jump now back to SQL Server, and I will show you one thing. So we have this non-partitioned table. I will just put it into the picture again, right? Where the data has been ingested in more optimal way. It has slightly different number of rows, but it shouldn't matter here. It's still around 37 million. But as you can see, the compression is a bit better compared to my original table. So this is because we made the row group sizes more optimal as per the documentation. So after discovering that, I came to conclusion. So maybe I should do the same in Postgres, and 7-day chunk size is not optimal as well. So what I did, I created additional table with just a fraction of the data, but bigger chunks, and I wanted to verify if the compression ratio is getting better with those settings. So here's my table. Here's the query. I call the table monthly. I have only, sorry, typo. Here it is. Right, so as you can see, we have more data per chunk as compared, but the compression ratio is the same as in the original table. So no gain here, as opposed to SQL Server. Okay, so let me quickly jump to our presentation to summarize things. Right, so storage efficiency. In SQL Server, our uncompressed data is around 2.5, 2.7 gigabyte. And the compressed one, we've managed to achieve 700 megabytes, which gives 30%. Postgres timescale statistics show that we have around 5 gig versus 1.2 gig, which is around 25%. So this is comparable. Okay. So having done that, I think we can move into data ingestion process. I'll jump here. So a few words about how the data was ingested, how the data was put into the database. So this is available for free. If you want, for example, Yahoo Finance offers, you can download the data from them if you want to use market data. So I have pre-download a set of CSV files. Each one of them contains 1 month of data, and I was using Python script with pandas library to load the data from CSV into the data frame, and then using SQL Alchemy to get the data to push the data into database engine. So let me quickly show you this whole process. That these are my scripts. This is my script. I will run it now. I have 4 tabs here, 1 tab for each table, which I'm gonna kick off now. So this will run in the background. It won't take long to do. This is ingesting. So while this happens, I will already discuss the results of my previous data ingestion, because I've loaded many of those files already. So usually they had around 500,000 rows, ranging from 5 million to nearly 500,000 to 700,000. And this is how how long it took to load each file into specific table. So this all looks pretty much the same. The difference isn't big, right? There was only some spikes for loading to Postgres row store. Not sure why that happened, but it happened. It doesn't change the overall picture that it took around a minute or slightly over a minute, depending on the size of a specific file. And this gives like probably 7,000 to 8,000 rows per second, which is not bad, but I realize this can be done way faster if you use a dedicated technique like timescale copy functionality or bulk copy into SQL Server. You can probably achieve a speed of 10x faster, or even more, like more than 100k rows per second. But this was not my goal. My goal was to compare the ingestion with the same technique used for both engines, and it seemed quite the same. So timescale seems the fastest one, but as you can see, there's seconds difference. So yeah, this is an example, right? So our Postgres raw data, 640,000 rows ingested in 100 seconds, 96 seconds, hyper table, SQL raw 100 seconds, and pretty much the same the column store. Okay. Back to our demo. So now I'm going to showcase you what's happening when we ingest new data. So we should get some open row store groups. Here they are, right? So these are the partitions that we just inserted data to. Again, it's not optimal because we have low number of rows in each, but we have those row groups open versus the older ones, which are compressed. We can remove that condition, and then we will see and use only our table. Eliminate those two from the picture. There you go. So all the rows are compressed, those are open. Let's take a look at Postgres. So there's also a query to see that, and let's find out if we have uncompressed. So is compressed equals false. We have only one for our hyper table here, which is, and we've been inserting, which I think I didn't say that, we've been inserting data for April this year, for the whole month of April. So it seems that it compressed the chunks, some of the chunks already, and left only the last week uncompressed. Yes, exactly that. Okay. Ingesting the data, and now let's see if for any reason we need to remove the data. Updates to the table, column store compressed table are not recommended because this requires our engine to go and decompress stuff, change the data, compress it again, and this is expensive and inefficient operation. So let's see what happens when we need to remove the data. I'm going to remove the data that I have just inserted. I will first do the uncompressed one. Oh, brackets are not necessary here. So let me remove them. It doesn't like brackets. Oh, I must have copied that from SQL Server. Sorry about that. Public. Okay. We have removed the exact number of rows. That was pretty quick. How about this? Okay. And yeah, we deleted it. It's even faster. It was quite quick. Okay. Same operation in SQL Server. We're gonna remove the uncompressed and then the column store one. Meanwhile, I'm gonna mention that we have a control of some kind of control on our compression, and we can manually trigger compression of the chunks that are still open, or the row groups, I should say. This is the command. So we need to alter index, reorganize. We can point the partition number we want to compress, and with compression all row groups on. So if for some reason we find that partition is open and our query is mixing row store with column store, then we can go and force this compression if need be. So it deleted our rows. Let's do same here. So we have that clean. Okay, so we are back to the previous state, and yeah, we are ready to move on to the next topic, which is aggregation. Any questions so far? I think
no questions so far, so you can go on.
Okay, I will move on. Aggregation. So the core of analytical queries. I have the time and CPU statistics on, which I use those commands to have it, right? And here's my query. So I'm aggregating data for the closed price for each symbol for each month, right? Actually, this is not the most elegant query, because let me go here. This is exactly same query, but SQL Server 2022 introduced some new syntax. If you don't know, called date trunc, which looks much more friendly. So we're gonna get 6 months of data, first half of 2024, in this example, from our column store table. I have also enabled the actual execution plan to be visible when I run the query. I'll do that now, right? So let's give it a moment to execute. So our query came back in around 8 seconds. It returned nearly 2,000 rows. So we have six entries, 6 rows per each symbol, representing the price, average, max close, minimal close for each month, for each symbol. Right. So what do we have in those stats? We can see that SQL Server have done around 5,000 logical reads. It says LOB, which stands for large object binary reads, right? It didn't do much physical reads. It efficiently done read-ahead reads, which is good, and it used 6 segments. The important thing also happens here in the execution plan, right? So this is the total number of rows it considered useful. So 3.0 million, around 10% out of all rows we have in the table. It went for the batch mode execution, which is quite typical for column store, and we have our results here. Let's move to our row store table, and let's run exactly the same query for the same dates. It's getting the data for us. It took 9 seconds, so very similar. It did bigger number of reads, so 300, over 300,000 reads. Jumping quickly into the execution plan, it also used the batch mode, but the number of rows is way higher, so it's reading effectively the whole table. Okay, so let's see how it looks. Here. Aggregate. So we will use the syntax called explain analyzed buffers to have some insights into what's happening while Postgres is getting data for us. We have exactly same query. We group by month and the symbol and the same dates we use, right? So the important thing to look at. So the number of rows, it's exactly the same because we're using same data, almost 2,000 rows. When we use the explain, it does not show the actual results set, just our query plan, and it reads well over 300,000 buffers for us, which is a lot. It was using parallel sequence scan, which is quite expensive. So yeah, and it took, how long it took? Almost 10 seconds. So similar. Let's take a look at our table here. Okay, so it's way faster, less than 2 seconds. Same number of rows that you can see here. The number of buffer reads is significantly smaller, only almost 13,000. It used those partial group aggregates. The thing is that our output here that analyzes what has been done is way longer, because for each chunk we have same data being shown. Important thing to look at is it uses sequential scan on compressed data, and the custom scan, so-called columnar scan here, right, which is much more efficient. I have also one thing more that I would like to show you is I have here a Grafana dashboard that I built for both of those servers. On the left-hand side, you have our Ubuntu server. On the right-hand side, you have Windows server. As you can see, this is live recording of what we just did, right? So this was happening when we queried the SQL Server raw data. So we had reads of around 140 megabytes per second, right? This is our Postgres raw data, which gave almost 55 megabytes per second. I don't believe we really can observe column store reads or CPU hit because it's minimal. I can run those queries once again and observe it as we go. So let's start to see that I'm not lying. Okay, so let's start with the raw data in Postgres, uncompressed table, around 10 seconds again. You should see it coming here, right? So this spike represents that exact query that has been run. CPU-wise, it was like almost 15%. Let's do this one again. All right. Probably we won't see any spike here because this read should be minimal. It's refreshing every 5 seconds. I cannot make it more frequent, sadly. So I think we can rerun our queries in SQL Server. So the column store one again. And there you go. 7 seconds this time. This represents CPU while we run it, but no disk hit really. Up and back to Management Studio and our uncompressed raw data query. Same time again. We are back to Grafana. Probably we'll see the spike here. CPU, nothing here. Okie doke. No spike here. Oh yeah, I think I know why. I haven't done the buffer clean, right? So it didn't read this data from disk. It was all cached. So that's why we didn't see the spike. just to confirm that, I will run it again, and let's move on.
Michal, there's a question in chat.
Yeah, I just noticed now. So background optimization process similar to SQL Server tuple mover for time series workloads. Yes, there is a process that works underneath and moves and compresses the data. And we define that by our compression policy. I will show this in a moment. It creates a job. I'm not sure we can control this job, but it is there, and we can see even how frequently it runs. This tuple mover in SQL Server is not really visible to us. We know it is there, but we cannot see it. Okay, so conscious of time, I will move on to something called continuous aggregates, which is a big advantage of timescale DB. So what is it? On top of our table, hyper table, we can create materialized view. So the same query we used, we can convert into a view, which I did before, and we can run it. That's the query we have called. The view is called monthly closed. I'm gonna run for exactly same dates. Let's have it. And now you can see it's crazy fast. It's milliseconds, right? The number of reads is absolutely minimal. The number of rows is different because I use different dates. So let's fix that. We had almost 2,000 rows. Okay, let's fix that. Yes, still super fast. So why that happens, right? So this materialized view pre-aggregates this data for us, and it is sitting out there, just ready to be to be queried. So if we have a scenario in which we need to call something like that, a typical query against our time series data that repeats very often, then we want to convert it into materialized view, then the query becomes extra cheap for the engine and extra fast for the users. We can apply an automated refresh policy for that aggregate. We do it like this. I have this policy already in place. So we define that the behind the scenes it runs every hour to look if there's any new data that it can compress, and it goes back to 2 years from now, and it seeks for any new data or data changes, and it goes and refreshes the aggregate for us. If for any reason this is not enough and we ingested the data, we want to have immediately this materialized view refreshed, we can call refresh continuous aggregate for the specific time range that we are interested in. So when I first saw it, it kind of blew my mind how fast it is. So I thought, well, SQL Server has materialized view. Why won't I use it in SQL Server and give it a try? Which I did. So I will share my findings here. I created a view. I will do it as we go. Won't take long. This is how it looks. This is our query. I'm creating this here, right? So to make it materialized, I need to create a clustered index on top of it. Yeah, let's go. But it didn't work. Why it didn't work? Because it does not allow us to use average in our materialized view. So there's some kind of limitation. It suggests using sum and count big instead. Okay, so we can give it a try. I'm dropping the view, I'm creating it once again. I will use sum. Okay, the view created. I will attempt once again. It also doesn't like max, and I can spoil that it doesn't like min as well. So there are limitations that we cannot overcome, and we'll have to live without our materialized view in SQL Server. Obviously, we can work around this in a different way. So, create physical tables with a job that will collect those aggregates and make it fast for user and not heavy for the engine, but it requires some extra work. So the last point is, how do we maintain all that? So this is our weekend view. So timescale DB is pretty easy from that perspective. So all those policies that we can create are just simply creating jobs for us that run in the background, and we don't need to worry about it. As we ingest more data, the chunks are being created automatically. There's no job behind that even. We can see the job history. If anything fails, I think here that's a different job that failed in March. That doesn't matter here. We can add our retention policy that will automatically drop the data, in this case older than 10 years, from our hyper table. We can also manually drop the chunks, which is fast operation because it works on the metadata only. There's no real data deletion behind the scenes. Talking about SQL Server, there's a bit more to it. So as I mentioned at the beginning, we have to manage partitions, so create new partitions. Sometimes we need to merge partitions. We can also truncate partitions, which works similarly to drop chunk in Postgres. This is also metadata operation, which is very fast, and so on. So we have to be conscious of this extra work that's involved, maintaining your partitions. Let me run this and show you. This is our partitioned columns to table. So we have data in our partitions. I have pre-created partitions up until end of this year. If we approach this date, we will have to think about creating more partitions. If we don't do that, all the new data will be dropped into the last partition we created. So if we have tons of data, and by the nature time series data is not several millions rows as I'm showing you in our demo, but it's more 100 millions and billions of rows, and then it really matters. Also, I have to mention that column store index has some extra limitations around partitions. So you cannot, if you have data in your last partition, you cannot no longer split partition to create new ones. I will quickly show you. So let's assume we have we have some data at the very end of our partition, and we want to run this statement to create new partition in 2027. This is going to fail, right? Because the last partition is not empty. So we effectively would have to either drop this data or switch out partition to an external table which has exactly same schema and indexes. Run this code again, and then switch the data back. This is possible. I even wrote an article about that, on how to do it on scale. because I hit this problem back in the days, which was pretty painful. Yeah, so this is it. I will quickly jump to our my presentation. So this is the summary of our aggregation queries, which I collected before, but this is pretty similar to what we saw. So SQL Server was slower, talking about column store versus timescale DB. I didn't even mention the materialized view, so the continuous aggregate, which was crazy fast. I'm comparing the direct queries on the table. Still, SQL Server doesn't look that bad. It is slower, right? For the raw tables, this is comparable, right? As you can see, the disk usage was way heavier when we have row store. So this just shows that column store is dedicated for time series aggregate queries, and we have significantly lower footprint when it comes to disk utilization to serve our queries. Yeah, so key takeaways. SQL Server requires, something dropped here, requires extra attention when it comes to design, as I explained in terms of ingesting the data. Performance timescale DB for our data set seemed roughly 5 times faster, plus those continuous aggregates, which are unbeatable here. Compression, well, my impression is that on our data set it was comparable. Timescale DB requires less maintenance. We don't need to worry about those partitions maintenance. I think we need less knowledge around how it all works underneath. Cost. No, SQL Server isn't cheap, obviously. Here we have open source, but if we can consider enterprise support for timescale DB and Postgres, it's also not cheap. I didn't compare that here because it's quite difficult to get numbers for Postgres support. I think different companies offer that on case-by-case basis, so difficult to compare those here. And which one to choose? Pretty much based on our ecosystem and the expertise we have within the company. If we have a group of experienced SQL Server professionals, then SQL Server is an option for time series data too. That's what I think. Yeah, so if we have an enterprise ecosystem that already has SQL Server, we have the license, we are Windows first organization.
Michal, how much more content do you have?
That's almost done.
Okay.
Yeah, I'm conscious of that. This is the last slide. And we rely on HA solutions that we like in SQL Server and other features. Then SQL Server, I think, has something to offer in terms of time series data too. However, timescale is more targeted. If we are considering greenfield projects that we can build from the ground up, then probably timescale would be way to go. And yeah, that's it. Slightly overrun. Sorry about that. Happy to answer any questions if there are any. And again, you can scan my contact details here, and you can reach out to me after the session if you would like to. Special thanks to Thorsten Strauss, who helped me to prepare myself for that session. I hope you liked it.